Okay, great. So let's see. Yes. Okay, there is some latency. Hi, everyone. Nice to see you all here. Some of you I know, others I don't. I hope I can have the pleasure to meet you later on at lunchtime or later. My name is Giovanni Gualdi. I'm the founder of Deep Vision. Somebody of you may have heard about this company earlier, somebody not. I hope that in the next half an hour or so, I will deliver you some content so that you will be also able to appreciate what we do in my company. First of all, thanks to all the organizers, thanks to EBV, of course, Gianluca, Nicola, and all the others, and also for the patience from you, because it's, as Gianluca said, it's lunchtime. But I will do my best to take and capture your attention. I have a very minimal style, so not much text, no fancy graphics. I will try to catch your mind and keep you aligned with my talk. Before going into the, let's see if that, oh, yeah, okay, yes. Before going into the talk of today, as you saw by the title, is about 3D and AI and at the edge. That is a quite peculiar, I would say, mix of three technologies, three enabling technologies. I would like just to spend a few words about the company. Since day one, it was basically 12 years ago, our mission was to deliver added value to our customers through computer vision solutions. We have a great team. It's multidisciplinary. There are engineers, mathematicians, physicists, data scientists. Along the years, we have been very proud of a long list of customers we put together from across all kinds of industries. We are agnostic to the industry. Logistic, security, automotive, medical, agri-tech, traffic, intelligent transportation, and others. And we have an important list of partners. The latest one that was established just a few weeks ago is with Halo. So we are official software partners with Halo. And probably today you will understand also what was the endeavor we had and we carried on to then become Halo partners, and also some important awards. We received an award from NVIDIA 4 years ago for tackling the topic of doing deep learning on synthetic data. Today, Marco mentioned something about that. Okay, so that's enough. Before moving on, I would like to make a poll just to understand who's in front of me, who has a technical background that is still alive in his profession today. Who is technical here can raise the hand just to understand how many. Okay, okay. So I would say more than 90%. Second poll, who still writes code today? Okay, so 70%. Okay, so great. Computer vision is, through AI, of course, I mean, with deep learning, has been really successful on the visible domain. There is, I mean, it's obvious, and with basically the same task that go on and on, more and more solution gets still created just by classification, detection, segmentation, recognition, and if you add time on it, you can do some further stuff like tracking, action recognition along the time. However, the point, and if you think all these are connected to main questions, because after all, if you think computer vision is reverse engineering, right? You need to understand things back from what is happening. Something is happening and you want to get it. And these are the who's, right? The four who's. But however, if you think that there are contexts, there are industries and cases where the visible domain is not enough. And it's not a matter of how deep and how great is your AI. The point is there a signal? Because if there is no signal, there is nothing to extract. You can just get noise out of it. So, and of course, this is obvious, but I mean, not so obvious, because it's quite common that you see networks and people investing time in trying to get signal out of some data where there is no signal at all. So the point is that sometimes you need to use other data, different data than the visible. There is, of course, a whole bunch of other spectrums you can use. I mean, you know all of them, of course, because you are technical guys. And you can even use, with multispectral cameras, you can use more than one spectrum. But we are not going to talk about that today. That's not the point. There are other domains. Other domains where, I mean, computer vision is not just about the visible spectrum, is not just about other spectrums, it's also about tackling other domains. And the 3D is I would say, the major one, aside the reflectance of light in the several spectrums. But there are other domains that are emerging, and we shouldn't neglect them. Think about the event cameras. Who heard about event cameras before? Okay, some of you. So you should pay attention to this type of cameras. These are cameras. They are also called neuromorphic sensors. They have extremely high rate. We are talking about several thousands or tens of thousands of detection frames per second, even if they do not deliver really frames. And extremely high sensitivity, 4 times higher than the human eye. So, but today we'll stay focused on 3D and why 3D is relevant. So I listed here a set of industries where 3D is absolutely relevant, and some cases where you cannot really do real stuff, real solutions, if you don't have 3D. How can you do real collision avoidance if you can only say that there is something in front of you, but you do not really understand where exactly? It's just in front of you, a bit to the left. Is that enough? Is that what you really want for collision detection? Or what if you want to do data augmentation for cool digital marketing, where you want to show some dress or virtual dress or virtual eyewear, and you are not able to measure the real size of the person, so that you then ship the wrong size of the eyewear or of the dress. So you understand, I mean, all very different industries where 3D is totally relevant. But, you know, hunger comes by eating, you know. So 2D is cool, 3D is cool, so why not having both of them? And I just want to give you a very simple use case that makes it so easy to understand why having both sometimes is nice and sometimes is not just nice, is necessary. What you see here is an example of application for measuring the pupillary distance. And I can tell you that you cannot do that either only with 2D or 3D exclusive. No, you cannot. You need both. Because with camera, with the 2D camera, you can detect the pupils quite neatly, in a very precise manner, the center of the iris, and then you go to the depth and you do the metric measurement. You need both. But there is something slight behind this, that is the syncing. 2D and 3D data is really valuable if it is synced, because what if there is no spatial alignment? Can you put together these two information if you have not the guarantee about the spatial alignment? And what if there is a time gap between the two data? I mean, if you're using two sensors, and what if you didn't pay enough attention to have the two sensors synced in time? And there is dynamics in your scene. So you understand that having 2D and 3D is cool, gives you, expand the range of your opportunities, but you need to pay attention to syncing. And for some sensor technologies, the syncing is native. For other sensor, it is not. So don't give it for granted. Don't underestimate the importance of doing that and design it properly. I'm creating the base of knowledge and of agreement to move to a step further. I want you to agree, or at least to understand why I bring my point. 3D is important, it's not a game, it's important, it's necessary in many use cases, and if you have 2D, it's even better. So regarding 3D, I would like to just check with you together the main groups of technologies that are out there. The first one is active. The second one is passive. I mean, first and second is not a degree of importance. Active means that you project a signal into your environment and you measure the signal back. And through this transmitter and receiver, you measure the distance. And therefore, you have 3D information. And the passive, on the other hand, is exploits what the environment already gives to you without any need of artificial signals to be projected into your environment. They are both very used. The active one, this is a list of active technologies. We spoke a lot about LiDARs in the first talk. But there is also time-of-flight cameras. I mean, they are quite similar technologies because both measure the time of flight of the light or the phase. But there are other approaches. Here you see a point cloud produced by a leader. And active technology is really and widely used in the industry today. But there is no clear winner with the passive technologies as well because they both have pros and cons. The passive technologies are most of the times related to vision, and that is what we will talk about today. Stereo cameras through geometric triangulation or extraction from motion. You basically create your 3D by having one sensor that moves a long time in space, and other niche approaches that are not very widely used. And of course, if you do a good job, you can recreate with your stereo camera. We have here a little tiny stereo camera. Still, it's a stereo, even if the baseline is very, very narrow. And if you do a good job, you can create your depth map that is a point cloud because it's metric measurement. I intentionally, both groups have a common point together. They measure the distance, and for each sensed point, they provide the X, Y, Z coordinates of what is measured through principles of physics, geometry, optics, whatever, but it's a measurement. And even this, you could give it for granted, but it's not. And you understand in a moment why. Because what is the third group? A lot of emphasis on it. It's improper, what I wrote here, but I want to put it here because it's getting more and more attention lately through what we see around, is what I could call predictive 3D technology, where you have depth that is produced by a single image. Could be in the visible spectrum, could be also in other spectrums. Honestly, I mean, what you see out there all work in the visible spectrum, so that you take an image and through whatever method we will see later, you produce depth. I want to spend some time over it, otherwise you cannot put in the proper perspective the real 3D. Not that I want to put one on top of the other. It's not that one is better than the other. They are just different in nature. Monocular depth is not measurement, is inference. It's inferring, is a method purely based on AI that embeds some prior knowledge. I mean, this pointer is completely useless. Embeds some prior knowledge into a model and exploit that prior knowledge to produce that depth. And it just does what we do when we cover one of our two eyes, and we still understand, we have a sense of the depth, even with monocular vision. We can do that, and the network does actually the same thing. But it's very important to understand the difference between measuring, because it's designed, intentionally designed to have a signal that is correlated to distance, or inferring, that is semantic. And this means that the prior knowledge gives you a strong dependence on the context that you used in training. You are completely tied to the context that you had in training. And the other thing is that it measures up to a scale factor. So if you look at the math behind it, you will see that the loss and the metrics are scale invariant, logarithmic errors, scale invariant. So you measure up to a scale. You have no clue about the scale. Yes, still, but if I cover my eye, I can understand that you are at 3, 4 meters, 5 meters, not 100 meters. True, but I will bring you a couple of examples to let you clearly understand what I mean. About context dependence. What if I take this image, I rotate it, I pass it to the same network, and the result, I flip it back. If it's a measure, the result should be just the same, right? Unless numerical errors. Do you agree, right? This is what you get. You get a completely different depth estimation. And you clearly understand that if the one on top, okay, so I move very slowly, okay. The one on top is somehow seems correct, even if to really understand the correctness, we should plot it in a point cloud and navigate through the point cloud. But the one on the bottom is absolutely wrong. And that's why, because the prior knowledge embedded in the model didn't take account for rotations, for example. But this is just a proof of concept. You understand how dependent you are from the context. And what about scale invariance? How big is this bench? I already gave the keyword. Well, 3 meters wide, 4 meters wide, 1 meter high. Yes, typical. But what if the next image is like that? Okay, well, there is something that is confusing my perception. Either the bench is big, or there is a little tiny bike on top of it. And of course, you can put it in perspective only when you see this. You see a person there, and you understand that this is a huge bench. But I tell you, if you provide the image on top to one of those depth, a mono-depth method, you will get totally the wrong scale. Take all this information and put it in your perspective, put it in your industry, and understand if monocular depth can does the job for you or not. But what we want to do now is to dig deeper into real 3D through stereo vision. Who knows about stereo vision a bit? Can raise the hand? Okay, 30%, something. So stereo vision has some pros and cons. Let's look at the pros. Well, first of all, low cost. It's true that LiDARs are getting lower and lower in cost. However, industrial grade LiDARs with the longevity still cost a few $1,000s. So it's, I mean, and the technology is always evolving. So if you do an industrial project and you need to look forward, you don't really know if your technology will become obsolete soon. On the contrary, stereo vision is a quite mature technology, and the cost is quite low because electronic is simple, it's off the shelf. You just need regular cameras. I mean, they need to have some properties, but just regular cameras that you can find out there. They provide solid measurements because there is geometry behind it, and the geometry, I mean, 20 years ago they were saying that in computer vision the geometry was a solved problem. It was quite a strong sentence, but still, the measurement is solid because of what lies behind. You can have very high resolutions in your point cloud, depends on the resolution of your sensors, and cool, it is natively synced 2D and 3D because you produce the 3D out of the 2D imagers. So you have, for free, perfect sync in space and time between 2D and 3D. And that is not to be neglected. But of course, it's not a perfect technology. The range compared to LiDARs is a bit more limited. LiDARs can reach even 100 meters or more. Stereo cameras, it depends very much on the geometry of your imagers, but it's definitely within the range of a few tens of meters, not 100 meters, unless for military applications with huge baselines. It is sensitive to stress, mechanical and thermal, because you have to do a calibration that is quite sensitive to the stress that the camera could suffer at operation time. And there is the risk of sparsity in your 3D, because, and we will see why with a picture. And the last point is that it's computationally quite intensive. And that's not true for example, for active technologies where computation is much lower. How can you cope with this? Well, regarding the range, you need to do a proper geometric design. You need to understand what is the principle behind it, so you need to stay within the perimeter, functional perimeter of geometry, but you need, after you have properly designed geometry, and also properly design your case, the robustness of your case, you can cope with these two crucial points. But what about the risk for sparsity? So I bring here the traditional stereo matching algorithm. What does it mean, stereo matching? Many of you know, this is for the others. It means to have an algorithm that correlates left and right view, and depending on the differences, you understand what is, you get the measure of the distance. It's just what we do in our brain automatically with our two vision sensors, the eyes. And SGBM, semi-global block matching, is a traditional approach based on image processing. And as you can see, it's not complete, the image there. Why? In this case, it's just because of the ambiguities given by the lack of texture, because there are areas where the texture is not enough to create this matching. But there are other ambiguities, other source of ambiguity. It could be blur. There is no motion here. Everything is nice and static. But what if there is blur due to overexposure or high dynamicity or out of focus? That increases the risk of sparsity and also visual adversities. What if there is dust that degrades your texture? What if there are particles flying around, like in the agriculture? Or what if there is noise coming from the sensor? Or rain? So what I want to bring here is that AI really can help in this. And I'm not talking about AI in the monocular fashion. I'm talking about AI that takes the best out of the two, that takes the best out of signal that contains geometrical information, that is the left and the right image, and takes the best out of the prior knowledge, because it learned how to model, a bit like the monocular was doing, to model the depth of semantic. So I see a chair in front of me, and it cannot be 20 meters away. Still, I have also the geometry supporting my choices, my answers, my results. That's the point. And here you see the network we produced in division that is applied to the same image and that takes geometry and prior knowledge and is able to fill the sparsity, basically, that was left from the traditional approaches. You see that the image is completely filled up in every single corner. And this is the 3D that is behind that disparity image. Disparity means the difference between the left and the right. And this is metric. This is not up to a scale. This is metric. And by the way, you probably have seen that in the demonstrator in the back, but later on you will, so that was not part of the slides. You will see in the back later in the demonstrator live. Cool, so it seems that we tackled also, by the way, I forgot to mention an additional advantage. With AI, you can also cope with, in a certain manner, also to the to stress over calibration, because the semantic can help you to cope with this slight misalignment over the two imagers. I'm talking about slight stuff. I mean, I'm not talking about huge differences, but it can cope, whereas the traditional approaches cannot at all. If the cameras are uncalibrated, lose calibration, you need to calibrate them back again, either online or offline, but still you need to do that. But we didn't talk about computation. If you go on the public challenges for this kind of things, you see some AI methods for doing stereo matching via deep learning, but you see that, I mean, I took the, just for the sake of this presentation, I wanted to get refreshed, and I saw the best 10 methods, avoiding the anonymous ones. Just compute on RTX 3080 or V100 GPUs or A100 GPUs, so server-grade GPUs, massive power consumption. Is that what we want? Maybe yes, but what if you want to have a programmable stereo camera? It's possible to do at the edge, and that's what we want to bring in here, in this workshop. That's what we did. And this is what you can see in the back. This is the computation with the network I've shown earlier, 3D plus AI, running on the Halo accelerator, hosted on a Raspberry Pi, running at something like 10, 15 frames per second. And look at the power consumption. I mean, the Halo is hosted on a Raspberry Pi, so an ARM. And by the way, the CPU is not doing much. It's not doing much at all, because it's just doing the rectification and passing the images to the inference. And you see a big difference in FPS between the Raspberry and the Intel, and it's not because of the computational power of the processors. It's more about the bus, because the Intel has 4 lanes Gen 3, while Raspberry has 1 lane Gen 2 PCI Express. And as you understand, there is a lot of exchange, because we are talking about massive models with a lot of parameters that needs to be transferred to the accelerator for every context. But I will not go too much in detail. So if you want to see it live, just come in the back later and we can play with it. And I want to show you the GStreamer pipeline. It's very, I mean, many of you work with GStreamer. It's very, I wouldn't say handy, but it's very useful. It's not handy if you are a, but it provides a lot of blocks, a lot of plugins already accelerated. And in here, you see the simple pipeline to produce what we saw up above. What is cool is that you can even, on the Halo, put an additional network that, why not, is working on the 2D image. You have a native alignment, that's for free, let's use it. And you can see that we just put, for the sake of the demonstrator, an object detector on RGB, but you understand that as soon as you have an object detector on the 2D domain, you can measure, you can do metric measurements on those objects through the 3D. Okay, so, I mean, Raspi is cool, but NXP is in the room. And Raspberry is not in the room, so I want to also to put some emphasis on what we did on the IMX8 and Plus. Massimo Incerti spoke about all the details about it. We had the privilege to put our hands on top of the 8M Plus since even before the official release. We played around a lot with the NPU. I mean, it's 2 teraops. Maybe it's not as gigantic as Halo. Still, I mean, you can do a lot of stuff with those 2 teraops of acceleration. And you shouldn't see the acceleration over the 8M Plus as an alternative, as an exclusive OR with the Halo. You can see them in combination. And I'll show you why if you come later back to the bottom of the room, and I will show you the thing working on the IMX8M Plus. But there is not just the NPU, there is also hardware encoding and decoding, and we have put all this together. So basically, we have a GStreamer pipeline that uses the hardware decoding so no cost for the CPU, decoding 2 video streams, by the way, exploits the Halo for the 3D reconstructions, and exploits the NPU for other tasks on 2D, on the 2D image that you can put together. So just to keep your curiosity alive, I will not show it here. If you want, you come later on to check it out. And for those that are in streaming, just drop an email and we can open a discussion with you. Okay, so I think I reached the end. 3D plus AI is the solution we created and that I just described. We deliver it as a software IP. Stay tuned to this page because we'll publish updates in here. And that's it. Thanks.